Good morning, good afternoon, and good evening. Thank you for joining Open Data Lake Day on Google Open Source Live. This is a monthly series of sessions led by open source experts from Google and community leaders. We really appreciate everyone taking the time to come here together digitally to learn more about Open Data Lake. My name is Priyanka Vergadia, and I'm a developer advocate here at Google. I'm based in Mountain View, California, and today I'm joined by TJ, my co host, to take this open data journey with you all.
Hi there, my name is TJ. I'm a product marketing manager here at Google. I can't wait to co host today's amazing event covering all things related to open data lakes. Priyanka, can you please tell the folks at home what's in store for them today?
We have some really interesting topics today. If you're looking to learn more about Open Data Lake, you're in the right place. We'll kick it off with the talk from Amr Awadallah, VP of Developer Relations, walking us through how to break down innovation and cloud barriers with open source. But before that, we have a couple of housekeeping items, TJ.
Don't forget to put your questions in the live Q&A forum below the live stream window. Speakers are ready to answer your questions live. If you're viewing in full screen, you'll need to exit full screen to see the live Q&A forum. Our sessions have been recorded to allow for accurate transcripts and so that speakers can focus on answering your questions live. And once we're done, don't forget to join us at the after party on Google Meet. You'll see a button to join in the events page at the end of the last session. Oh, and last but not least, use the hashtag GoogleOSLive to share your experience on social channels.
With that, enjoy!
Hi, my name is Amr Awadallah. I am the VP of Developer Relations for Google Cloud. I am so happy to be joining you today to talk about open data lakes and how open source is breaking down innovation and cloud barriers. I want to start by sharing a personal story about the first time I saw the value of data lakes. It started when I was the VP of Product Intelligence Engineering at Yahoo in the mid 2000s. Our team was responsible for analytics across a number of Yahoo's key products. As the amount of data grew, we started to run into significant scaling issues with our traditional data warehouse. We had one query in particular that we jokingly called the monster query that ran every night. It was a simple aggregation query, but it had to join two massive tables representing all the views and clicks across all of Yahoo's products. That's when the Yahoo search team showed me a newly born project called Apache Hadoop, which was based on principles from the Google MapReduce and Google File System papers, GFS. When we migrated the monster query to Hadoop, we not only accelerated it significantly, but we also were able to rethink our data strategy overall. Everything was different, from dynamic data schemas to being able to query any type of data, including unstructured data like images and text, and query that data in any way, not just SQL. We could do processing, machine learning, etc. And the economics were just outstanding in terms of the per byte costs. We were no longer bound by the rigid nature of our data warehouse, which was frankly better suited for financial reporting, but not necessarily product innovation. This new thinking was the beginning of the term data lake. We just didn't call it that yet, which essentially means the ability to store any type of data, then process it scalably in many different ways, not just SQL. In late 2008, I left Yahoo to co-found Cloudera, and it was immediately obvious that a lot more is needed beyond MapReduce. Let's walk through a few open source moments that helped make open data lakes what they are today. After the Google papers were turned into Apache Hadoop in 2006, the ecosystem around open source big data really started to take off. Apache Hive, which was started by Facebook, allowed users to issue SQL queries without having to worry about programming MapReduce jobs. Next came Kafka from LinkedIn, which provided a scalable, high throughput, low latency platform for reliably collecting and processing real-time data. Wow, that's a mouthful. In many ways, Kafka enabled batch data lakes to go real-time. And last but not least, Apache Spark, which was started by Matei Zaharia at UC Berkeley. Matei was actually the first intern at Cloudera in late 2008, and he worked on a number of the very core issues of MapReduce. Matei very quickly recognized a fundamental problem with the MapReduce staging that he aimed to solve by caching data more intelligently. As a consequence, Spark was born, and it significantly accelerated processing times for data lakes. While the open source ecosystem continued to innovate, the cloud market continued to gain momentum. So let's take a minute to see how open source projects like Apache Spark made its way to the cloud. Open source software in the cloud all started with VMs in the early days, which is still a preferred method today. We swapped out physical machines for virtual machines so enterprises could scale faster and be more agile. Then containers appeared on the scene. Containers provided a significantly lighter weight way to encapsulate applications versus virtual machines. And that freed up a ton of storage, memory, and networking resources. Not to mention that containers are much easier to work with than VMs, at least that's what I think. That then led to Google's creation of Kubernetes, which is an orchestration system for automating container deployment, scaling, and resource management. Given that data lakes are resource heavy, this naturally led to Kubernetes very quickly intersecting with these open source projects. Many of these projects now have versions that leverage Kubernetes directly for resource management. Google in 2019 launched a Spark operator optimized for Kubernetes. At Google, we use Kubernetes to power our largest data applications, and now enterprises that have Spark-based apps can do the same very, very easily. And finally, serverless is the next wave that we are seeing emerge. Developers want to focus less on VMs or Kubernetes clusters for that matter, and more on building analytics and data applications that make a difference for their business. Serverless helps by allowing them to set parameters for their applications, and then the cloud automates everything else for you. While how we run open source data lakes in the cloud has changed, so has the vendor community. Open source vendors like Cloudera, Confluent, Databricks, etc., have helped accelerate cloud-based solutions and made it easier for enterprises to depend on these open source projects. While cloud continues to become the default option for many new open source workloads, the principles of the community around openness still remain key. And it's super important that as you look to build an open data lake, you build that on a truly open cloud. So what does this mean? 1. The cloud needs to support the open source projects you care about. This is not only about open source software, but more importantly, open data formats. You need to make sure that your cloud of choice supports the purest version of open source to avoid vendor lock-in. We'll touch on that later on in the presentation. 2, the cloud you choose needs to support multi-cloud and hybrid. An open data lake strategy should support any environment by default. There are 2 parts to having a data lake that can run anywhere. 1, you can access data across environments with open source software of your choice. And 2, you can code once, then run anywhere. The final piece of an open cloud requires a partner community that builds for the cloud. This is important if you ever want to quickly extend enterprise-grade support for the open source software of your choice. Without a partner community, you risk creating a walled-off data lake that you can't extend when your business needs to change. These reasons have been a major driver for enterprises to move to Google's open cloud. Organizations like Major League Baseball, Vodafone, and Pandora have already made that move. Major League Baseball supports 30 teams spread across the US and Canada, and they have millions of fans around the world. They process and analyze extreme amounts of data and run workloads in the cloud as well as at the edge, with on-prem data centers at each of their ballparks. By leveraging Kubernetes, they containerize those data analytics workloads and run them in the location that makes the most sense for the application. Sometimes situations arise where they have to do computing in the park because it would take a long time to upload the 8K videos to the cloud. This allows them to quickly deliver the stats in the stadium to the fans, to broadcast, or to the scoreboard. To give you an example, if something were to happen during a broadcast at the Yankee Stadium, they could shift that application across the city to Citi Field, where the Mets play, and continue broadcasting without interruption, assuming the Mets fans don't mess with those servers. Lastly, if they had many stadium failures, they can upload that data to Google Cloud and process it there. That's a hybrid data lake for you. Next is Vodafone. Vodafone serves 625 million customers in 66 countries. As part of its digital Vodafone transformation program, the company is working with Google Cloud to build a global big data platform. Vodafone's existing on-prem data platform consisted of 8 clusters with more than 600 servers, and that platform lacked the agility or scalability to support the business. So Vodafone built Neuron on Google Cloud to solve this issue. It's their version of a cloud-based data lake that will replace their legacy environment. The insights from Neuron are being used to support a wide range of applications. For example, Vodafone's gigabit networks are increasingly optimized by AI to push capacity to where customers need it most. And real-time analytics enable Vodafone to push personalized commercial offers to customers, such as data top-up, when they are most likely to buy. Scaling to this size is not an easy task, and Vodafone has done an amazing job so far. Now, Pandora. Since its founding in 2005, Pandora has made data the very heart and soul of its business. To date, Pandora has created 13 billion stations for its users, who listen to its content on more than 2,000 different types of devices and give a digital thumbs up or thumbs down to whatever they are hearing. This feedback is critical to the advertisers and recommendation algorithms. Now, this example hits close to home because just like the monster query I mentioned to you at the beginning of the talk, they too had a monster query, which they called the night job. It was running impressions for advertisers and was taking 5 hours to process multiple petabytes of data on their legacy infrastructure. Now it takes a bit more than an hour on Google Cloud. These companies are innovators. They are rethinking how to build open data lakes across all environments. Now, I want to take a moment to acknowledge another great innovator of our time, Dilbert. I'll give you a second to read this slide. It's very relevant to the topics we are discussing today. I'm looking at it myself. Joking aside, I always like to have a slide like that to get people looking at a different tab to come back and look at at me. So hopefully you did look at the slide and you did see the tab. This is definitely one of the funniest Dilberts I have seen on the topics of containers and Kubernetes. With that said, let's move on with the program. I've had the opportunity to talk to many industry-leading companies across the world. Now, I want to share with you the 4 common reasons influencing these companies to have open source as a key part of their data lake strategy. As you look to make a case for open source in your own organization, it's important to talk about these points. Number 1, freedom of choice. Too many enterprises have become locked into vendors that push proprietary data formats and black box analytics. Open source offers a way to build on top of community standards so that if your vendor of choice is not living up to your expectations, you can quickly port over your data and apps to another vendor, even if that new vendor is you, and you decide to self-manage your own open source. We at Google embrace that freedom because we know that this means we will retain you as a customer, not because you are locked in, but rather because we continue to deliver significant value and innovations to you. Number 2, multi-cloud, hybrid, and edge support. When you use open source, you can have your data lake analytics live across multiple environments, not just a single environment. Just like we heard with the MLB story, open source software and advancements like Kubernetes makes this even easier. Now it doesn't matter where your data lives. You can quickly exit or even quickly move your data applications to a completely new environment without having to re-architect, re-implement, or transcode all of your data from one format to another. Number 3, community and innovation. There is a ton of new innovation that comes out of the open source community that spans multiple organizations across many industries. From patching security risks to building new analytical techniques, we truly believe that a well-run open source community can move faster than any single organization can ever move. That explains why you see Google continuing to contribute many projects like Kubernetes, TensorFlow, and others to the open source community. Number 4, build a creative outlet for your team. Engineers love working on open source projects. Just like a poet wants to share their work with the world, so do engineers. It's also important to note that as employees move from company to company, they can still contribute to the same projects that powers your data lake. This means you will still benefit from them even when they leave you. So while I wrap up, I want to leave you with 2 final thoughts. 1, open data lakes are the future, but it is a journey that takes time. So don't wait, get started today. Whether you just migrate one use case or all of your infrastructure like Vodafone and Pandora, you won't regret how open data lakes can truly transform your business. And 2, make sure you pair your open data lake with a truly open cloud to gain control over your destiny, innovate faster, and allow your applications to run anywhere. Thank you for your time.
Thanks, Amar. It was really interesting to learn about the evolution of the Apache Hadoop ecosystem from someone that was there from the start. Next, we will hear from Brad Myro about scaling out deep learning with Spark. Take it away, Brad.
Hello, everyone. It's so awesome to be here. My name is Brad Myro, and today I'm going to tell you a bit about how you can do distributed deep learning with Spark. So just to briefly go over the agenda, we're going to first talk about Apache Spark. We're then going to talk about distributed deep learning. We'll then talk about using Spark for distributed deep learning, and then we'll talk about how you can get started with it today. So with that, let's just dive right in, and we'll start with Apache Spark. So now, what is Apache Spark? Well, taken straight from the Apache Spark website, it is an open source tool for doing unified analytics engine for large-scale data processing. It features doing this data processing in memory, and the APIs exist in Python, Java, Scala, and R. One of my favorite things about Apache Spark is the fact that the parallelization is more or less completely abstracted away from you, and the resource management and all of that, Spark handles for you to make these distributed jobs much easier. And within the last year, Spark actually introduced native support for GPUs, which makes this super relevant for the machine learning and deep learning world. Spark was released in 2014 as part of the broader Hadoop ecosystem. It more or less exists as a successor to Hadoop's MapReduce. And so as such, you can run it on top of Hadoop Yarn. Spark has seen a tremendous amount of growth within the last 7 years or so, with the 1.0 release again in 2014, but then the 2.0 release in 2016, and then the 3.0 release last year in 2020. And Spark is being used for all sorts of different exciting problems across a very large and continuously growing community, and it's a really cool framework. So the way that Spark works is that it features what effectively functions as a master and worker model. So the worker nodes each contain different pieces of the Spark distributed job. So each one of these contain executors, which contain separate tasks. And so you can actually configure how many of these tasks you'd like to have happen at any given time via some of the Spark configuration. Now, in order for you to actually submit your Spark jobs, you interact with Spark via a Spark context on your driver. This driver can be on your own machine. This can also exist on the master machine of the Spark cluster. You have options available to you, but this is essentially how Spark works underneath the hood. Speaking of Spark underneath the hood, there are 2 main ways that Spark actually stores your data in memory. So the first is the original one, and this is called an RDD, or a resilient distributed data set. And the way that this works is it features an unstructured means of actually maintaining the data across the nodes. And then the newer way to store your data is using a data frame, which is similar to other data frames that you might have seen in other data processing frameworks, but it allows you to interact with your structured data in a tabular sort of way. Now, the Spark ecosystem is super rich, and you have a lot of options available to you in terms of tools that you can use on top of it and runtimes. So we'll start with the ecosystem. One of the first tools over here on the left is Spark SQL, and this lets you interact with your Spark data in memory using SQL queries, like you would in a relational database or the like. There's also Spark Streaming, which lets you do transformations and data processing on streaming data that is managed by Spark. There is MLlib, which is useful for doing machine learning on top of Spark. And then there's also GraphX, which lets you do graph algorithms using the Spark framework. If you go down to the runtimes, here we have 4 different runtimes available to us. So the first is Spark Standalone, and this consists of Spark's own resource manager and scheduler that is separate from any other piece of software. But then there's also Hadoop Yarn, which has, as we mentioned, Spark originated within the Hadoop ecosystem. So you can use Yarn, you can use Mesos, and then you can use Kubernetes as well to run Spark on top of. Spark contains a rich set of data visualization tools. So the way that Spark actually executes jobs is it does it in what's known as lazy execution. And what that means is that once you provide Spark with a command that requires returning data, it will basically wait until that point to run the different pieces of the pipeline. So what this DAG visualization tool on the right here will show you is effectively the query plan that Spark comes up with when it's going to execute a job. So that's for the DAG visualization. On the left here, we can actually see the different steps and how long that these steps are taking. So this is really useful for debugging, because let's say your Spark job is taking a long time and you want to figure out why. This will actually show you how long each step of the process took. It can help you debug. And if something failed, it can show you where the job actually failed. And this really gives you a lot of useful information. And again, this is all part of the Spark Web UI that comes with Spark out of the box. Now, Spark is able to interact with a lot of commonly used data sources within the community. So, of course, you have CSV, JSON, Parquet, and Avro. You also have access to data in a blob store, such as Google Cloud Storage and Amazon S3. You can also access data in HDFS. You can access data using Iceberg and Delta Lake, as well as data warehouses such as BigQuery, Snowflake, and the like. Spark also is commonly used within the machine learning community. So we briefly mentioned Spark MLlib earlier, which has a fairly similar interface to scikit-learn for those of you who might have used that within the Python community. And then there's also other tools such as XGBoost and Rapids that really focus a lot on somewhat more traditional machine learning methods. And so later on the talk, we're going to talk about how we can use Spark with distributed deep learning. But before we get to that, let's actually talk about what distributed deep learning is. Before we get to that, let's talk about what deep learning is. So what is deep learning? It is a branch of machine learning that focuses on a subset of algorithms known as neural networks. This name might sound familiar to you because they are loosely based off of the way that the neurons in our brain interact. These neural networks have seen a lot of success in being used with image data, with natural language data, as well as structured data. Now, fundamentally, deep learning relies on a lot of complex mathematics, such as calculus, linear algebra, differential equations. And while a lot of folks in the deep learning community will disagree on how much math you do really need to know to get started with deep learning, the reality is that a lot of this is abstracted away from you in some modern day frameworks such as TensorFlow or PyTorch. Now, another caveat with deep learning is that as your models get bigger, as you begin to add more and more neurons, they can generally perform better, but they do require using more computational power. And you need those larger machines, you need more machines to be able to actually create the models that you would like to create. So why is that? So let's say you're using a single machine to try and train your job. Well, the idea here is that optimizing linear algebra is actually fairly computationally expensive. So that's one problem. Another problem is that as these models get larger, they might not actually fit into the memory on your machine. And that can also become a problem. And if you have something like a modern day laptop, it might be hard to actually upgrade the hardware in there. I know I personally can't on mine. So that can be a problem. And also, as you're processing training data, you might realize that this becomes time consuming, especially if you're constrained by the hardware on a single machine. But as you start to add multiple machines, a lot of these problems end up resolving themselves in such a way. Given that linear algebra is parallelizable, you can scale that across the multiple machines in your cluster. You can take a large model and actually split that across multiple machines, so you're not limited to the memory on a single machine. And to generalize, you can get near linear additional performance per machine. So the more machines you have, the better, because you're just able to speed up your training by that much. Now, when you're figuring out the hardware configuration for your setup, so every machine is going to have memory, but every machine is going to have CPUs. But there's you have to figure out the considerations between the CPUs that you want in your cluster and the GPUs that you want in your cluster and on the machines within those clusters. So let's talk about a CPU, the central processing unit that is on every device, including the device that you are watching this from. So CPUs are great at doing general purpose programming. They let you open your favorite IDE. They let you watch videos. You can check your email. You can use text editors. You can do whatever you want, and that is thanks to the power of the CPU on your machine. And because of that, they're designed for a wide variety of use cases. Fundamentally, operations on a CPU do happen synchronously. And because of that, you generally, a lot of machines nowadays have multiple. So, your machines might have 2 cores or 4 cores. Even phones nowadays have multiple cores on them. And that's because you can chain these together and, parallelize the data processing that way. But now when we look at GPUs, well, these are literally designed for the parallel processing of information. And what they're really good at is doing mathematical computations, especially matrix algebra that you might see in something like linear algebra. They're most commonly used for distributed machine learning. And like CPUs, you can also use multiple together. Even though you're able to parallelize your tasks on a single GPU, the more you have, the better, because that's just, you can continue to add parallelization onto that. So if you're just starting out doing either machine learning or deep learning, you're probably starting out on one machine that has multiple CPUs on it. For instance, it could be your laptop. As you begin to scale up, maybe you'll get a nicer laptop or a desktop that has a GPU on it. Maybe you'll get a desktop that has multiple GPUs or a machine that has multiple GPUs. And then, once you continue to squeeze as much value out of that as you can, you then might want to upgrade to multiple machines with multiple GPUs on them. And again, the more you add, the more computational power that you have, the more efficient that your model training is going to be. It's going to be faster, and in some cases, it'll just be able to train in the first place within some reasonable amount of time. So when you're doing distributed deep learning, there's 2 sort of paradigms that generally occur. One of these will generally occur as you're training your model. So the first way to train a model is what's called the synchronous method of doing this. So the way that this works is that it actually takes an entire model and it will split it up across multiple machines. So in this instance, you will take, with 4 workers, you'll take 25% of your deep learning model and put it on each one of those machines, so that at any given point, the entire model is being trained on 25% of the data. So for instance, on the left node, you'll have 25% of the data trained on 25% of the model. And then as you keep going, it'll be another 25%, another 25%. And this just ends up going in a circle. And that's how you end up training the model synchronously, but also in parallel, since all of the data is being trained on a different part of the model at a given time. And then there's also asynchronous, which introduces this concept known as the parameter server. So this is a centralized location that is actually keeping track of the parameters and the values in your model. And the way that this works is that each one of these workers contains a copy of the entire model and is training on a subset of the data and then sending the updates to the model back to the parameter server. And they're constantly talking to each other and getting updated so that they can all stay in sync with each other. So now that we've talked a bit about Apache Spark and deep learning and distributed deep learning, and just a bit about the benefits of why you might want to do deep learning in a distributed manner, let's actually now talk about how to do deep learning on Spark. So Spark, as we've discussed, is perfectly suited for doing distributed data processing. And with the recent built-in GPU support, you're really able to get a lot of awesome processing power out of Spark using the full capabilities of hardware that are typically used for machine learning and deep learning nowadays. So one really nice benefit of this is that you're actually able to combine your data processing and model training environments just into one using CPUs and GPUs. And then on top of this, in 2021, there's a lot of open source projects that are available that allow you to actually do this. And, a lot of companies are working on this sort of technology, and we're going to talk about a few of those open source projects momentarily. So traditionally, when you're building a machine learning pipeline, you'll generally have two separate environments for doing your data processing and for your training. And the reason for this is that really up until, within the last year or so, you couldn't really use GPUs a whole lot for doing data processing. Traditionally, if you had, let's say, a Hadoop cluster, this is really going to focus on a cluster of machines that are mostly CPUs. And that it's fine, and it totally works, and it still works. But because of that, you generally would have a separate environment for using your GPUs and doing machine learning. And so that requires generally, pulling data out of, let's say, your data lake, your data warehouse into your data processing environment, then writing it back into, writing it somewhere so that it can then get loaded into your training environment. And now I'm not about to suggest that you shouldn't necessarily keep these decoupled, but because of these new advancements within the Spark community, you have the option to do one environment. And in some cases, that's going to be preferred because if you're dealing with a lot of data, you might not want to necessarily read and write all of that between tasks. There are definitely some advantages to doing that, and there are some shortcuts to be able to do those efficiently, but you at least have the option. Or if you want to maybe play on with a subset of the data, you can do everything in one place. And on top of that, if you're maintaining this yourself, it's one less hardware setup that you need to necessarily worry about. Or if you spent, a huge investment on a hardware cluster and you want to be able to use it for as many things as possible, well, now you can use it for both your data processing and your deep learning. So you have the option there, and I think that that's really great. Okay, so now that we've covered how you can use Spark for deep learning, let's actually talk a bit about some of the tools that are available to you to use within the open source community. So 3 projects that I'm going to talk about briefly today are the Spark TensorFlow distributor, TensorFlow on Spark, and Hadoop. So the Spark TensorFlow distributor is a newer tool that is maintained within the TensorFlow ecosystem itself. TensorFlow on Spark is maintained by Yahoo and Hadoop on Uber. Now, all 3 of these tools provide similar functionality in that they allow you to take the TensorFlow code that you already have and just distribute it across a Spark cluster. So I've included an example here, or a generalized example here, of how you can do this using the Spark TensorFlow distributor. So here you're going to import the distribution strategy that you want to use. In this case, you're going to use the mirrored strategy runner, which is going to be similar to the asynchronous model in that you're going to have the model just mirrored across each one of your machines. You're going to take your TensorFlow code, you're going to wrap it within a training function, And then you're going to just submit that function to your Spark cluster, which is wrapped within this mirrored strategy runner. You can also state how much you would like to parallelize this. In this case, you would do it, or in this case, we're suggesting that you should do it with 4 different parallelization tasks. And you can change this depending on what your hardware configuration looks like. So now I mentioned, all 3 of those frameworks can more or less focus on just taking the TensorFlow code that you already have and distributing it. Horovod comes with a cool tool known as Spark estimators. Now, these are specialized objects that let you literally take the same the same data that you're working with in memory and then just pass it into a model. So in this case, we're able to create a Keras model here, and then we can take that and just pass it into the Keras estimator and have all of the training occur within the same pipeline, but also being able to take some shortcuts and use the functionality that the estimators provide themselves, which can sometimes just make things a little bit easier. And TensorFlow on Spark and the Spark TensorFlow distributor do have some other fun tools around them that make them super user-friendly and just work really well. So I definitely encourage you to look into more of those if you're interested in learning more. So that's all I have. Thank you so much for hearing me talk about Spark and distributed deep learning, and I hope you enjoy the rest of your day. Bye now.
Thanks, Brad. Sounds like a classic good news, bad news situation. Good news, your models are running faster. Bad news, less time to play some ping pong while your models run. Next, we'll hear from Roderick Yao about open table formats and Apache Iceberg improvements. Take it away.
Hello, everyone. Welcome to my talk. So today we're going to talk about open table formats, as well as some of the updates in the Apache Spark community. First of all, a little bit more about myself. My name is Roderick Yao. I'm engineer and product manager here at Google Cloud. I've been here at Google a little over 4 years. Before that, I've been working in a series of big data companies throughout my career. So today's agenda, first we're going to introduce what are table formats. And then we're going to talk about a few of the available ones that can get access on top of GCP. Then we're going to deep dive into a little bit about Iceberg. And then we're going to introduce some of the most updated features that I've been working on in the community. So first of all, what is the table format? A table format is a way to organize data files into form a structured table. So the most typical file format you can think of is actually Apache Hive. It used to be the only way that organize data into a data lake or an enterprise data warehouse on top of Hadoop. But it has some inefficiencies. So we're going to talk about that first. So on the left is a high-level architecture for Hive, where client access to a Hive server, which is actually the front end that handling the Hive queries, and change these queries into logical plan and physical plan, et cetera, et cetera. On the left side, there's a Hive Metastore. So basically all the table metadata, such as partitions and data file locations, statistic, all stored in Hive Metastore. Is actually backed by a relational database. On the right side, all these actual data files are organized into a tree-like structure and put into this storage system. So we used to be, most of these are running on top of HDFS. Nowadays, a lot of the Hadoop cluster are actually running on top of cloud, and the storage system being the cloud storage. Usually you see an object storage type of systems. On the right side, it's a typical structure of a Hive table. So in this case, I put it on top of HDFS. You will see a /user /hive /warehouse. And then under that, there's a database, DB1, 2, 3. Under that directory, there's table. Under that, there'll be partitions. Under that will be data files. So this whole design poses a few issues, especially when it comes to the cloud storage type of world today. So first of all, the structure is actually a work against the recommendation on most of the object stores. Because, for example, we organize data into a year, then a month, then a date kind of partition. If we want to access all the data within, let's say, 2020, there are going to be a lot of requests that go into the same prefix, which could cause hotspotting on object storage. On top of that, there's a lot of listing operations to get all these partitions and find all these data that's stored inside of each partitions. There's not really transactional support before Hive Asset, but even Hive Asset is introduced, it actually uses the same kind of data directory structures. Second point is isolations. One of the annoying problems that with Hive is that a reader can read the data while you wouldn't know there's a writer is actually writing to that table or appending data or partitions to that table. So your read state could be unknown. It's also common practice for adding or dropping partitions on HDFS to a Hive table, which actually breaks that atomicity and also breaks table statistics. Breaking that table statistics will cause inaccurately calculating the query plan, which cause performance and scalability issues as well. As we talked about earlier, listing operations on object store is slow, but Hive actually needs to O(n) level of listing calls, where n equals the number of partitions. And Hive also needs to open a lot of, let's say if we were using Parquet files, it actually need to open a lot of Parquet files underneath that partition to find your data, which is kind of slow on the object storage as well. There's a lot of other problems. For example, large tables could accumulate huge amount of metadata in itself. It's actually hard to parse. So there are other issues for Hive. We talk about the table statistics. Another kind of common pain point is the physical layout. So where we construct the table, let's say by partitioning by day and hours. If that user doesn't know the physical layout of that table, the user could very well be passing the where filter by a timestamp, where in this case actually results into a full table scan. Some other issues that Hive doesn't support, things like lineage, history, and the schema evolution type of requirements. So now we talk about Hive. So let's look at what the trend is happening in the data lake world. So as data storage becomes cheaper and cheaper, people are thinking like, hey, maybe we can use some of the database kind of technologies and database features inside of a data lake. So these will be typically like a data quality ask. Data lake used to be treated as a raw storage for a lot of companies. So the user will put into unprocessed data, so not so high quality data gets put into the data lake. Then when you retrieve that, you have to clean it up. So that slows down all these processes of gaining insights out of the data lake. Another part is we talk about the transaction and isolation. There are other requests around data management, especially like things like schema evolution, data lineage, et cetera, et cetera. So there are a couple of table formats that are available on top of GCP. We actually ship Delta Lake. We support Apache Iceberg as well as Apache Hudi. But today we're going to mostly focus on Delta Lake and Iceberg. As you can see through comparison, these two storage table formats pretty much have more similarity than differences. There are, of course, other angles they can compare, but all of them supports really ACID transactions, schema evolution. It's a structured data format. You can roll back to history, look up history. you can do time travel access. So let's take a look at Delta Lake, how it actually achieve all these characteristics. Delta Lake uses transaction log to achieve these features. Basically, transaction log is kind of similar to Red Hat logs, where all the change operations come to be queued and write to the log first. So this gives you a couple benefits. First of all, is being a single source of truth. So the log become this like a truth where all the views that derive from this log are consistent. So the user won't get a fork of content. It also guarantees atomicity. So inserts operation, updates operations are either complete or not complete. So being not complete being not inside the transaction log. So there's no intermediate unknown state. So in the diagram below, kind of give you a simple illustration how this happens. So in the first commit, the operations that we did add a bunch of data. That data results into 1 and 2.parquet files, and they are being committed into a commit file called 1.json. And in the next batch of operation, we remove all of these data, we add some more. So we remove 1 and 2 parquet files, and we added a new 3.parquet, and that results into another commit files. So when Iceberg, to get the current state of that data, we'll just pretty much go through this process, replay all these commit logs, and you can later roll back. You can look up history, you can look at lineage, and even evolve the schema. So here's the structure, how it looks like on the storage system of a Delta table. There are two main parts in each of the table. There's this data part, there's actually transaction log part. The data part is shown above, where it has the partitions and data. Of course, partitions are optional. So as we talked about earlier, so on the transaction log, there's a lot of commit files. As you can see, all these JSON files. So each commit will create a new commit file. When there are many commit files, Delta will then create the checkpoint files, which is the example in the below. A checkpoint file really represents that state of that table. So as you can think it is pretty much like rolled everything before that into one checkpoint file. Checkpoint file can be a great way to achieve to increase the efficiencies to lookup. So you can just look it up to calculate the current state of the table. You can just look up the most recent checkpoint files. You could or may not have a few more commits after that point. But if you do, you pretty much just get the latest checkpoint file and replay all the commit files happen later than that. And you can also track data that no longer being used. So for example, I don't care any data that being written or hasn't changed like 30 days ago. I can purge those data as well as the metadata associated with it. So now let's look at another really interesting project, which is Apache Iceberg. So let me start on the top of this structure. So Iceberg also provides ACID transaction. So let's take a look at first how to actually achieve that. And then we can look into some other characteristics, how it actually being so efficient to handle table schema and some of the partition nuances. So on the top, where you have a reader and have a writer. So the reader is reading, the writer is writing to a new place. So Iceberg uses this concept called snapshots, where there's also a current snapshot pointer, which in this case is actually pointing to snapshot 2, where that reader is reading. And while the writer is creating the next new snapshot, when it finishes, it'll switch the pointer to the new one. So there's some benefits to this kind of design, is that there's no need to lock the whole storage system in order to do a write. So where readers can continue to read from the current snapshot consistently without any of the new data that is happening in the next snapshot. And you can, all these changes to the data files and stuff is atomic. So basically, appending cross partitions, merge, and rewrites, these are atomic operations. Iceberg added a lot of the table schema, partition layout, statistics into its metadata. All the metadata are immutable, so the history is linearly moving forward. Current snapshot, there's basically it's a pointer. It says 2. That can be rolled back to 1. If in some future days that is pointed to 3, you can always roll back to a previous state. So next we'll talk about how to commit. So when the writer finishes writing to, say, snapshot 3, it'll find the base version, which is snapshot 2, creates all these new metadata and manifest files, which we're going to talk next. Then we're just going to atomically swap the base version pointer to snapshot 3. Now, snapshots are split into multiple manifest files. Each of the manifest list files. Each of the manifest list files then will split into multiple manifest files. And the manifest files actually stores the pointer to data files and some statistics. These manifest files are being reused from different manifest lists and different snapshots to avoid the high volume rewrite. We'll come to that later. So let's look at the content of these metadata. So on the right side, this part is the manifest list file. So as you can see there, it contains manifest file passes, lengths and partition, lower boundaries, upper boundaries. The bottom part is actually showing when I'm opening up a manifest file. It has the data file location format, as well as some of the Iceberg tracking data. There are values to filter files for scanning. For example, there are partition like data volumes, values per column, lower and upper bounds. There are metrics for cost-based optimizations. So on the file level, these are row counts and file sizes. On the column level, there are value counts, the number of null values, as well as the size of that column. So these are very, very exciting characteristics that we just talked about for Apache Iceberg. So now, how to get it started if you want to run on top of GCP. So Apache Iceberg actually supports a two-way of putting your data in the table. So one way is relying on the storage system. So you can use something like a Google Cloud Storage or HDFS. Another way to store these metadata is actually inside of a Hive Metastore. So very conveniently on GCP, there's a Dataproc Metastore, which is a managed Hive Metastore. So after we created that, we basically get a Swift IP address and a port. So we can use that to connect Iceberg to our Dataproc Metastore. So this is the way you kind of start with the use the Spark SQL to connect. And you can pretty much create a table, and as long as you specify using Iceberg, then you pretty much your table is already being structured by Iceberg. So where you can insert values and query that. So next, these are some of the examples that I can show some of the Iceberg metadata access. So in the first query, we basically just query all the snapshots that is stored inside of this table. Then we can look up histories. Then we can also look up manifest files. From the talk above, I pretty much introduced you to the Iceberg concept and how to achieve some of the asset properties and some of the other characteristics. So now, as Apache Iceberg getting adopted more and more, the community is coming together, adding more features. So the top one is the merge into support. So now you can do upserts and merge data or even delete data into your table based on another source table. We can practice this in their example on the Iceberg website. You can try it. Second is to support copy on write and merge on read. These are different ways to support write to Iceberg. So the copy on write is a way to optimize for reading. So basically, it creates an entire copy of the data every time you write it. but it's, as you can kind of get it from the intuition, it's a little bit slower on writing, but it's optimized for reading. Merge on read is the other way. So where each of the write creates a Delta file until some point you merge these status into a full version of the data that is ready to be read. So this is really optimized for writing, where the reading part could be a little bit slower. Next feature is SQL extensions in Spark 3. So basically, this supports creating procedures. There are many like built-in procedures in Iceberg already for mostly management purpose. For example, you can roll back snapshots, set the current snapshots, expire some snapshots, remove some of the orphan files, or even rewrite the manifest files. There are also some procedures support migrating Hive or Spark tables into the Iceberg format. Next is, as we can kind of show a little bit earlier, the support for Hive catalogs loading Iceberg tables, in addition to just the Spark session kind of a catalog. The next one is still in progress, is the version 2 of the Iceberg format. Basically, the intention is to support row-level deletions. So with that, that kind of concludes my talk today. Thank you so much for listening. And my name is Dr. Yao. Feel free to reach out me there. And have a nice day.
Thanks, Roderick. It was great to understand the open table formats, Apache Iceberg, and the new updates to organize files that contain data in the form of structured tables. Next, we will hear from Zhao Feng about Scaling Hive Metastore with gRPC and Cloud Spanner. Over to you, Zhao.
Hello everyone, this is Joe Fang from Datasources Metastore at Google Cloud. In this talk, we will introduce several ongoing enhancements on Hive Metastore to make it more scalable, more robust, with more security features. The approach that we take is to bring gRPC and Cloud Spanner to Hive Metastore. At the very first, I would like to give a brief introduction to Apache Hive and the Metastore. The Apache Hive is a data warehouse software that manages and processes large data sets in distributed storage using SQL. The first release of Hive is almost a decade ago. It is built on top of Hadoop, and the SQL queries are translated into MapReduced jobs for execution. The Hive Metastore, which will be our focus today, it was an integrated component in Hive at the beginning, and it becomes a standalone module around 2017. In recent years, Hive also starts to support ACID tables, which support transactional semantics. Now, let's talk more about the Metastore. Metadata is a critical component in data analytics engines and data lakes. Metadata contains all the essential information to run data query and processing. For example, the table schemas of the data warehouse, location, partition information, and also statistic data to optimize queries. And Hive Metastore is a central repository of Hive metadata. Its usage grows beyond Hive and becomes the standard metadata service in the Hadoop Spark ecosystem. As shown by the picture, you can find that many popular software depends on or work with Hive Metastore. And the new open table formats, such like Iceberg and Delta, they are alternative metadata providers, and they can also be integrated with Hive Metastore. Now, let's zoom in and see how the Metastore works. The Metastore has two major components, a metadata server and a relational backend database. The server provides clients access via Apache Swift. This is an open source RPC framework that is widely used in the Hadoop ecosystem. As a result, the client can read, insert, update, and delete metadata through the Swift endpoint. The Hive are the clients. They are usually softwares like Hive, Spark, or Presto. The server itself is stateless, and it stores all the metadata in the database. Because Hive already has a history of around 10 years, so many new technologies has not been adopted into Hive. So this is where we plan to improve the Hive Metastore. So here are several pain points that we observed when we provide Hive Metastore as a service on the cloud. First, the Apache Swift, the Hive Metastore endpoint, it does not have all the features that we need. For example, service mesh such as Istio is a very important tool to manage the traffic to the Metastore, but it supports gRPC better than Swift. In addition, Swift does not support streaming API, which is very useful to read large data, such as list all the partitions of a giant dataset. The second issue is that Swift does not provide a general and easy to use solution for authentication and authorization. For example, identity and access. But identity and access is among the most important features demanded by Hive users, especially in a shared environment. Currently, Hive can support self-managed approaches, for example, Kerbals and LDAP for authentication. But those solutions, they are complex to set up and they need additional maintenance overheads. From the point of a cloud service provider, it also degrades the experience of a fully managed service, which means that the customer, they does not need to do anything other than just click a create button. Another thing about authentication is a fine-grained access control. This is another very important feature which is missing here. With fine-grained access control, a user can be authorized to only certain databases or tables, but not the entire metastore. This is a very useful security feature which we would like to add. The last pinpoint is scalability. So in a production environment, the rows of records in a Hive Metastore, it can easily grow to millions and even beyond. So the database now becomes the bottleneck of scalability. As a result, Hive users have to come with customized approach, such as scale the database, such as like data sharding or clean it up periodically. So all those solutions, they are complex and they are also error prone. Our solutions to the aforementioned issues is to bring gRPC and the Cloud Spanner to Hive Metastore. gRPC is a modern open source RPC framework, and Cloud Spanner is a serverless, fully managed relational database. It has 5 nines availability, so it can solve the scalability issue. Let's see how they can work with Hive Metastore in the following slides. We will first talk about integrate gRPC into Hive Metastore. Here is a list of all the benefits that we can gain by using gRPC. First, gRPC uses HTTP2 as the transport layer, and it uses protobuf 3 for data serialization. So it has a higher efficiency than the current approach that Hive is using, which is a Swift binary serialization and TCP or HTTP as a transport layer. And gRPC is also better supported by the service mesh, such as Istio. Also, in addition, gRPC has built-in authentication support. For example, it supports token-based authentication. And gRPC can be easily integrated with many cloud-native authentication frameworks, such as Google Cloud IAM. gRPC also supports streaming API, which is useful to read a large batch of data. And in addition, gRPC client and server, they can be extended easily by using the Interceptor API to add more functionalities. It It is very challenging actually to re-implement a Hive Metastore in gRPC. The reason is that Hive Metastore has over 100 API methods exposed by Thrift. It means that we have to rewrite every method again in gRPC. This is a huge amount of work, and even after we completing it, keeping the Thrift and the gRPC implementation code in synchronization is very challenging, especially for an open source project like Hive that everyone can contribute. To simplify the work as well as making it very maintainable, our idea is as follows. We keep the Thrift API and its implementation unchanged, but we add an additional gRPC proxy on top of it. You can find in this top picture, there is a client on the left side and a server on the right. So the server accepts Thrift requests, but the client sends the server gRPC requests. So to make it work, a gRPC to Thrift proxy is deployed together with the server. All the incoming gRPC request is firstly converted into Thrift requests. When a Thrift response is returned by the server, the proxy translated back to gRPC response and returned it to the client. So in this way, we can make the original Thrift Hive server work with a gRPC client. On the other hand, we also want that all of our gRPC Metastore server compatible with our existing Hive Metastore clients, which sends Thrift requests. Otherwise, our existing Hive Metastore clients, they have no way to talk to the new gRPC server. To do so, we need to do very similar things to the client as well. As you can see in the bottom picture, we need another Thrift to gRPC proxy that is deployed together with the Hive Metastore client. It operates in the reversed way. So it translates outgoing Thrift requests from the client to gRPC requests, and it sends the gRPC request to the gRPC server. Then it receives gRPC response from the server, then converts the response to Thrift responses, which are finally received by the Thrift client. So with this approach, by deploying a proxy on the server side and on the client side, we can keep the Thrift client and server unchanged, but now they talk to each other using gRPC on the network layer. This approach, but it introduces additional overhead, as you can easily observe here. So this is the overhead of the converting happening in the proxy layer. So the long-term solution is to replace Thrift entirely by gRPC, but it needs more time to get that far. The previous implementation is about how to design the proxy and make it work with client server. Now let's look more into the implementation of the proxy itself. Implementing the proxy is much easier than gRPC re-implementing the gRPC Hive Metastore service from the scratch. We only need to implement the conversion logic between Thrift and gRPC messages. So firstly, we manually create a protobuf file that has gRPC equivalent protobuf messages and also gRPC methods, which are the same as the Hive Metastore Thrift methods. As shown in the picture, this is an example. So on the left side, we have a Thrift message, and on the right side, we manually create an equivalent gRPC message. And at runtime, we use MapStruct, a tool that can automatically convert between Java objects with similar fields. In most cases, it can do the conversion automatically, and we need to manually handle several corner cases. We have an example here. So some Thrift objects, they use a list of objects as key. This is not supported in gRPC, so we have to create a new data structure in a protobuf to customize this conversion. After having this proxy, the next step is to integrate it into Hive, because even we have the proxy today, we need to manually deploy the proxies with client and server, which are not very easy to use. So in this phase, our plan is to integrate the gRPC support into Hive as well as other softwares which has a Hive client such as Spark and Presto. And this work will be contributed back to the open source Hive repository. You can find the details of our proposal in this link here. The idea is that we will first add gRPC configurations to Hive, very similar to the Swift configuration. So once gRPC is enabled by that configuration, a Hive Metastore gRPC service will be launched together with the original Swift server. Any gRPC request will route it to the new gRPC server, and the gRPC server now it plays the role of the proxy. It will translate the request to Swift from gRPC and forwards the request to the Swift server. In this way, the clients they can send a gRPC request and get a gRPC response, all through the new Hive Metastore gRPC service. And we modify the Hive Metastore client in the same way that it's controlled by a configuration. We will launch a gRPC client module together with Hive module, which is a proxy as well. After making this change, the Hive Metastore client we have is able to send out gRPC Hive Metastore requests. And fortunately, because Spark reuses the Hive Metastore client, so Spark can work with gRPC Metastore as well after using this new Hive client. The story for Presto is a little bit different because Presto implements its own Hive Metastore client. But fortunately, it only has a very small subset of Metastore methods implemented. So we can just go ahead and re-implement a gRPC client in Presto. Again, this approach adds additional proxy overhead, which will be mitigated by replacing Swift by gRPC entirely in future. This is all we have for the gRPC. So next, let's talk about what we do to bring Cloud Spanner to Hive Metastore. Cloud Spanner is a very powerful relational database. It is fully managed with 5 nines availability, and it also supports cross-region replication, which means that a user does not need to worry about scalability or database downtime anymore. Spanner also automatically shards data, and it also has an enterprise-grade security level. After we integrate Spanner with Hive Metastore, it means that when you deploy Hive Metastore in production, you can enjoy all the benefits here and don't need to work with any customized solution to scale the database anymore. Before looking into how to support Spanner in Hive Metastore, we checked the most popular backend database used by Hive Metastore, which is MySQL. But Cloud Spanner is very different from MySQL. For example, they are different in SQL dialects and also the functionalities like transactional levels. As a result, there are several additional work that we need to do to replace MySQL by Spanner. By looking more into that, we found that Hive Metastore interacts with databases in 2 ways. The first way is for most Hive Metastore tables, Hive will use data nucleus, which is an object relational mapping framework to read and mutate database in form of Java objects. Data nucleus, it uses gRPC to talk to the database. And for the other tables, which are newer Hive Metastore tables, which are added recently to Hive Metastore to support ACID tables in Hive 3, for those tables, Hive directly interacts with the database by gRPC, which means that data nucleus is not in the path anymore. To make Spanner work here, we need to support Spanner in both cases. Fortunately, Cloud Spanner they provide an open source gRPC library, that can be the bridge to access it from Hive. Our work here includes two parts. So the first part is to support Spanner in data nucleus. So this can be done by adding Spanner support into the data nucleus RDBMS plugin. We add the type information of Spanner there and also implement data nucleus adapter for Spanner. This is the first part, and after doing this, Spanner can work with data nucleus, which means that when you modify some Java objects, the corresponding data can be changed inside the Spanner database. The second part is to make Spanner work for the tables that directly accessed by Hive by JDBC. We add Spanner tables that are equivalent to Hive Metastore tables in MySQL, and we also modify the transactional handlers class in Hive to support it. After making those two changes, we can already make Cloud Spanner use in Hive Metastore. But because there are several differences of query optimization and the transactional support in Spanner and MySQL, we observed that there are some corner cases that are not work well in very large scale load testing, for example, with the TPC-DS benchmark. The first example is that the limit of mutations per transaction in Spanner is 20 kilo. So in this benchmark, there are tables with near 2 kilo partitions. It means that it may exceed the mutation limit when such tables are involved in the Spanner transaction. The solution to this is to limit the max number of partitions on the client side. For example, we can control this by Hive configuration of the dynamic partitions. We can also modify our Spanner libraries to shard partition mutations. Another corner case that we observed is that data nucleus may generate nested queries, but Spanner does not support nesting level larger than 1 kilo. The solution here is that we need to flatten the nested queries before sending the query to Spanner by modifying the data nucleus Spanner plugin. So all those are to-dos for us to make Cloud Spanner fully integrated with Hive Metastore, that it can be easily used without all those exceptions. That's all I have today. And to summary, we bring gRPC and Cloud Spanner into Hive Metastore to enhance its access point, authentication, and scalability. And those work, they are currently under development in Cloud Data Prog Metastore, and they will all be contributed back to the open source Hive repository. That's all my presentation. Thank you so much.
You can't build an open data lake without thinking about metadata management. So thank you, Zhao, for that amazing overview of the Hive Metastore. Okay, that's a wrap. It's now time for the after party. Come join us at the after party by clicking the Watch Live button on the events agenda page to be redirected to Google Meet.
Today's speakers will be also joining, and we will have some questions, interactive activities, and surprise guests. We hope to see you all there. Thank you.